Welcome to the Fractional Calculus seminar. We are happy to host today Professor Erdogan Medici, who has been a professor in the Department of Aerospace and Mechanical Engineering at the University of Arizona since 1989. Prior to joining University of Arizona, he worked at Northrop Corporation, Aerospace Corporation, and the Fraunhofer Institute. He has also worked at the KTH Royal Institute of Technology, NASA Langley Research Center, Sandia National Labs, and MIT as a part of sabbatical leaves. He is the lead author of 6 books on Peridynamics, available in Chinese and Persian, and finite element analysis. He serves as the co-editor in chief of the Journal of Peridynamics and Nonlocal Modeling, and an associate editor of ASME Open Journal of Engineering. He is the fellow of ASME and associate fellow of AIAA. Thank you very much for joining. You may please begin your talk.
Yeah, thank you so much, Pavan, for inviting me to give this talk. And also, I thank the attendees for their interest in this work as well. So basically, I'm going to talk about peridynamic differential operator and its applications. I'm going to give you an overview of what peridynamic theory is about, what peridynamic differential operator can do for you, and I'm going to show you some applications. From the beginning, I want to disclaim I'm not a mathematician, I'm an engineer. So those of you who are mathematicians, you may be more rigorous on some of the theory, but I'm just going to give you as I said, an introduction and flavor of what you can do with peridynamic theory. So here's the outline of my talk. Basically, I will go over the peridynamic theory, how it was introduced, and then discuss peridynamic differential operator, and show you quite a few applications related to the solution of differential equations, how you can do material failure modeling, some examples of multi-physics, and lastly, I'll show you some examples on how you can apply peridynamic theory to do some data manipulation. And peridynamic theory was introduced by Stuart Silling. He's a scientist at Sandia National Laboratories. And the first paper on peridynamic theory came out in year 2000. And the second paper, a generalized version of peridynamics, which is known as state-based peridynamics, came out in 2007. As you can see, for the first 8 years, there was hardly any growth in terms of publications. But then it really took off. You see an exponential growth in peridynamics. And originally, it was introduced to look at material failure, but then it found many different applications. As you can see in the pie chart here, it's in the area of mathematics, material science, engineering, different applications, data manipulation, machine learning. So you'll see various applications of peridynamic theory, and it's growing not only in the United States, but really all over the world, and mostly in China, as you can see from this bar chart here. So, and these are the applications that I just listed. Majority of the applications at the beginning was in material failure. Then it's very suitable for multi-physics modeling. These problems are challenging because you may have some moving boundaries, phase change, crack initiation, growth, and so forth. And multi-scale modeling is another sort of very nice application of peridynamics. So you can link various length scales. And solution to hyperbolic equations has been very suitable for that because you can manipulate the weight function so that you can manipulate how the information is going to travel, machine learning, and data manipulation. So what is peridynamic theory? It's really a very powerful mathematical framework for non-local description of equation of motion, any kind of field equation. And here you have a point x. Basically, this point x is going to be influenced by the other material points within this interaction domain. In this case, it's a sphere, and the radius of the sphere is going to serve as the length parameter, which is missing in classical continuum mechanics. Okay, so and as we'll talk about this later, but as the size of this, or the radius of the sphere approaches 0, peridynamic theory recovers the field equations that we have in local continuum mechanics. So it unifies mechanics of continuous and discontinuous media. So it's very suitable for multi-physics problems. the field equations or the equation of motion doesn't have any spatial derivatives, so therefore you don't have to worry about singularities. Okay? And the fact that this point X is going to be influenced by the other material points, we interpret this influence of other material points as the interaction of X and X prime within this neighborhood of this domain here. And so it really restores the non-local interactions. As I said before, as the sphere approaches infinity, you go to molecular dynamic simulations. As the sphere approaches zero, you go to classical continuum mechanics. And you can break these interactions. So if you want to initiate a crack or you want to grow the crack, you can break these interactions. Or you can look at phase change. You can give birth or you can kill these interactions to look at some phase change problem. So this is sort of a summary of what peridynamic theory is all about. And some basics here. So we have material point X. It's going to be interacting with another material point X prime. X has its own interaction domain. I'm going to refer to this as the family of point X. And X prime has its own family. It's going to be HX prime. And they could be arbitrary in shape and size. And X and X prime can be arbitrarily located within the interaction domain. Okay? And we're going to refer to this interaction between X and X prime as a peridynamic bond. So that's the terminology that we use. And as I mentioned before, this interaction may or may not exist. So if you have crack initiation, you basically terminate this interaction. If there is no crack or it's a continuous field, then this is intact, the interaction. So originally, Stewart-Silling introduced peridynamic theory to look at material failure. Okay? And by breaking a peridynamic bond, so here's this particular point X, it's interacting with the other points, and the peridynamic bond can be broken. If you break it, then it no longer carries any force, right? So you nucleate the crack, and the fact that you have only one bond broken doesn't mean that you're going to have a crack. So you have to have a way of measuring the local damage, and this is the way we measure it. So you look at the total number of bonds at the beginning, and then you look at the number of broken bonds. So in this particular case, as you can see here, this point X lost 50% of its bonds. So the ratio is about 0.5, number of broken bonds to the total number of bonds, about 0.5. Then we say you create a crack surface. And in peridynamic theory, the crack growth is also autonomous. So basically, we apply this particular criteria here to break a bond, and the rest is the same. So if the crack is going to go, if it's going to oscillate, if it's going to branch, if it's going to arrest, it's autonomous. So we don't control that. We don't guide how the crack should grow. And so that was 2007. That's the peridynamic theory Stewart-Silling introduced. And so in 2016, basically we were inspired by peridynamic theory, and a lot of the basics are the same. So we came up with this peridynamic differential operator. So basically what you're doing is differentiation through integration. Okay. So here, as you can see here, you have this function here. You multiply it with peridynamic functions. I'll tell you what they are. Over this interaction domain, that's the family of point X. And then you're going to let the interaction domain approach zero, like that sphere, the radius of that sphere approach zero, you're going to end up with the local derivative. Okay, so it's, and in general, you can write this for n variables, nth order, and it mathematically never blows up because we don't have any differentiation in integrand here. We have this internal length parameter, which is the domain of integration or interaction. And we still account for interactive nature of variables. We don't have any smoothness requirement. And we have a weight function in the construction of the peridynamic functions here. So that allows you to actually provide directional degree in the non-locality. And you can get very accurate higher order differentiation. So with this differential operator, you can basically write any local differential equation in its non-local form, both in space and time. So you can have non-locality in time as well. So how do we construct these peridynamic functions? Basically, we do a Taylor series expansion. And so these functions are orthogonal to each term in the Taylor series expansion, except for the term that involves the desired derivative. So that gives you this orthogonality condition. And with this, you assume a form for this function here, peridynamic function, and that satisfies the orthogonality condition. Okay, you can really choose the peridynamic functions in any form, it's arbitrary, but we work with complete polynomials because we can evaluate these peridynamic functions analytically for regular shapes. If you have a radius or a sphere, so you can evaluate them analytically. So then you end up with analytical expressions. So the as I mentioned before, the family size and the shape can be arbitrary, and the point doesn't have to be symmetrically located. So it could be near the boundary, for example, and you can have varying degree of interactions among the points. So you don't have to have one particular degree of interaction. Okay, here is sort of a derivation of peridynamic differential operator for 1D. Okay, so here's the function we have, and we're going to do a Taylor series expansion up to the fourth order derivatives. That's we get, and so I'm going to do this for fourth order. And what I do then, I take the peridynamic function, multiply each term, and then I integrate over the domain of interaction. And then I say, okay, if I'm interested in the fourth order derivative here, right? So this integrand should be equal to 1, and all the others should be equal to 0. And that gives me my orthogonality condition. And then once I know the peridynamic functions, you see I put it over here, then I can get the derivatives. So any order derivative up, in this case, it's going to be up to the fourth order. So by just multiplying this function here with the peridynamic function, taking the limit, is going to give me the derivatives. So it's very, very simple. And the construction, so in this case, I'm going to assume the peridynamic functions to be complete polynomials. So I have the fourth order derivatives. So I have fourth order polynomial here. And my orthogonality condition gives me this set of equations. And the unknowns in the peridynamic functions are these A1, A2, A3, A4. And the weight function, the degree of interaction, I'm going to assume it to be same for this particular case. And then if I take this, put it back into this equation here, evaluate, I'm going to end up with this set of algebraic equations. A is given in terms of this matrix here, shape matrix, and the coefficients associated with the peridynamic functions are given here. Okay. So once I solve for these coefficients, I put them back into the peridynamic functions, I go back, and I can basically evaluate the derivatives. Okay. So as I mentioned before, these peridynamic functions can be evaluated analytically for regular interaction domains. And here I'm going to take this point x, and it's going to be in between minus delta and delta, and x prime is the point that it's interacting with. Okay, and so I can evaluate these expressions here for that particular domain analytically, and that's the these are the peridynamic functions that I end up with. If I were to consider a second order Taylor series expansion, these are the functions I would evaluate. And in this case, I assume, just to make things simple, the weight function to be 1. Okay. So these are the functions we have. And then now I go back and I say, okay, let's say I'm going to substitute these peridynamic functions into the expressions that I showed you before. I'm going to, let's say I'm interested in the second order derivative. So here's my G42, that's the peridynamic function that I evaluated. And I'm going to integrate this, take the limit. I do these by using Mathematica. You can see here, I perform integration, take the limit, I end up with the derivatives. Okay, so I do this for all the way to the fourth order. So this is the way it works. And my next example is, let's say I'm interested in the derivative of a step function. And in this case, I do Taylor series expansion of up to second order. And I showed you G20, G21, and G22 in this here. These are the ones that I'm going to use. And my domain is going to be, x is going to be between minus delta and delta. And I will basically perform the the operation. So I integrate, take the limit, and then I end up with these values here. So as you can see here, the zeroth order derivative, which is the function itself, is recovered. If I take the first derivative, that's G21, I take the integration, take the limit, I end up with the direct delta function here. So that's very nice. Then basically, I mean, we don't want to do this analytically, but we want to perform, so we're going to solve these complex equations by using numerical techniques, right? So I'm going to construct these peridynamic functions through numerical methods. So here's an example. Again, I take this step function here. And if I perform my peridynamic function numerically, so I specify the horizon size, which is delta is going to be 3 times the grid spacing. It could be 6 times the grid spacing here. So when it is 6 times the grid spacing, my non-locality is stronger. As the horizon size is approaching 0, as I mentioned before, it's going to recover the local differentiation, right, in the limit. So as you can see here, for different values of delta, as delta approaches 0, it's becoming more like a direct delta function here. And also, you can take very accurate numerical derivatives. So here's a function, and we construct the peridynamic functions as I showed you before. You can take derivatives up to 4th order, for example, here, and you can see the error is very small. Okay, for even 4th order derivative, you couldn't achieve this by using finite difference technique, for example, 4th order derivatives, or even in the case of 3rd order derivatives. So it's very accurate if you want to take higher order derivatives numerically. Okay, so for 2D, it's the same story. Basically, we take the Taylor series expansion, we multiply each term by the peridynamic function, integrate over the domain of interaction, construct the orthogonality condition, and then we end up with the derivatives. And peridynamic functions is going to be complete polynomials. Again, I'm going to assume the degree of interaction to be the same. I end up with a set of algebraic equations coming from the orthogonality condition. Then I solve for the unknowns in this peridynamic function here that allows me to determine the derivative. So that's the same idea. Okay? And I can, for a sphere, I can evaluate those derivatives analytically. And for example, here you can see various operators in their analytical form, right? So this is, these are the analytical representations. And if you take these expressions and substitute them into the Navier's displacement equilibrium equation here, and you recover the same equation that was derived by Silling in 2007 based on the principle of virtual work. So we're going from the Taylor series expansion and the integral representation of the local differentiation, and whereas Silling started off because he's dealing with equations of motion, then he used principle of virtual work. These are the equations that he ended up with, so we can derive the same equations by substituting from here into this expression here. So I mentioned direction and non-locality. If you are solving hyperbolic equations, for example, the upwinding direction or gradient of travel time is going to be important. So your weight function could be, let's say, Gaussian, or it could be in this particular form. So it allows you to basically provide which way the information should flow. So this is a very nice feature of a peridynamic differential operator. I'll show you some examples of this. And discretization is straightforward. We use Gaussian integration, and you can have uniform discretization, non-uniform discretization, and you can have discretization both in space and time, or in space. So you can have non-locality, as I mentioned before, in time as well. And I'll show you an example of this this particular discretization. And the point in spatial discretization, it could be symmetrically located, but if you have space-time, it will never have a symmetric position within the domain of interaction, because in time, so the information is going to be coming from the past. Okay, so that's a nice feature of peridynamics. So convergence, people ask about convergence as well. So basically, the horizon size, right, as delta goes to 0, that's the interaction domain, we're going to recover the local solution, right? And if horizon is not approaching 0, so you have some value, that's really a non-local solution. What we do is we have this delta M convergence. So we let the grid spacing and the horizon approach zero. So then you have this convergence to the local solution. So this is the convergence study that we perform. And one other a nice feature of peridynamic theory is that you can impose periodic boundary conditions in a natural way. So you don't have to have additional constraints. So let's say you have this point here, x1, you have periodic boundary conditions here. So all you do is you bring this information from the right to the left to complete the horizon of x1. So that way you basically automatically satisfy the periodic boundary conditions. So for example, in the 2D case, I'm going to bring all this information from here to here, from here to here, and it's going to come from here to here. So then I complete the horizon of x1 and don't need to worry about periodic boundary conditions. So that's the way we handle periodic boundary conditions. So if you have a partial differential equation, let's say if it's this equation you have subject to some boundary conditions, how do we discretize? So we basically replace the second order derivatives with the peridynamic representation here. And you can see here G2 to 0. That means I have peridynamic functions associated with the differentiation with respect to x1 twice. And here, this one is going to be differentiation with respect to x2 twice. And that's my unknowns at each of those discretization points or peridynamic points. It's going to be phi. And the boundary conditions, I also write them in terms of the peridynamic representation. So here, for example, the first order derivative, G210 with respect to x1, and again with respect to x1, and so forth. So these are the boundary conditions. And once we discretize them, we put them into this set of algebraic equations, and these boundary conditions are enforced through Lagrange multipliers. Okay? So U here is a vector of unknowns, that's the field variable, and lambda is basically the Lagrange multipliers. And in this case, it's a two-dimensional study. This parameter AJ represents the area of each point that you have in the discretization. So that's the way we discretize, and I'm going to use the same approach for all the problems that I will show you, and everything is going to be the same. There's no fine tuning, there's no changing parameters, it's the same approach. Okay, so all of these numerical results that I have, I'm going to use the same approach. And in terms of the horizon size, or I'm going to mostly use 3 times the grid spacing. That's dictated by how you truncate the Taylor series. If you're interested in the fourth order derivatives, then your grid size should be at least 5 times the grid spacing. But that's like 4 plus 1. If you're interested in first order derivatives, then basically it's going to be 2 times the grid spacing. So that's the rule that we have. So I have these problems. I'm not going to go through the list, but as you can see, I have partial differential equations, and I have some problems related to crack initiation and growth, some hyperbolic equations, and then multi-physics problems, and then some data manipulation examples. Okay, so the first problem is it's a singular perturbation problem, so as you can see here, this epsilon is significant, right? So as it gets smaller, it's going to be difficult to construct a solution for this. But we just said, okay, let's take this. It's a second order derivative. Grid spacing is 3 times the grid, horizon size is 3 times the grid spacing. This 3 is 2 plus 1. So the highest order derivative you have here is 2. And that's why I'm adding 1 to this. So it becomes 3 times the grid spacing. That gives me computational efficiency and captures the non-locality. And so that's my boundary condition written in peridynamic representation. So this is the way we discretize, and I'm going to solve these equations. And as you can see here, as for a very small value of epsilon, it very nicely captures the solution from Mathematica. Okay? And that's the error measure. So it's simple, but yet it shows you the strength of the robustness of peridynamic differential operator. So the next problem is we have coupled nonlinear Burger's equation. And here we're going to discretize both space and time. Okay. And so this is my equation. These are my boundary conditions and initial conditions. We know the analytical solution to this problem, which is nice. Then we can compare. And I'm going to use the same sort of discretization for each of those problems. These are my peridynamic functions. And as I mentioned before, I have discretization both in space and time. So I have x1j and tj. So that's my discretization, x1 and t. And this is the second equation. And these are my boundary conditions. These are my initial conditions, right? And I have this now set of algebraic equations. These are enforced through Lagrange multipliers. And now I solve, right? So for U1 and for U and for V, then you can see the peridynamic solution and analytical solution at different time steps. Then we said, okay, let's make it a little bit more complicated. Now let's look at this Karamatov-Shvashinsky equation. You have a fourth order derivative here. It's nonlinear and periodic boundary conditions. Okay, and that's my discretization. I'm going to do implicit time integration in this case, and that's my horizon size 5 times the grid spacing because the highest order derivative is 4, and time step size is 0.8. That's the peridynamic solution. The details, the comparisons of all these are given in this paper, 2021. We looked at peridynamics-enabled learning partial differential equations. And we looked at various types of problems, but now I wanted to also show you that you can solve nonlinear Schrödinger's equation. So same idea, everything is the same, right? And I'm just trying to show you that you can indeed solve very complex nonlinear equations. And that's the peridynamic solution versus the reference solution. Then, so let's say you have a problem where you have a discontinuity, right? Here you have this single strand ceramic matrix composite. So this is a matrix, this is the fiber, and this is the interface, right? In ceramic matrix composites, the idea is the load is carried by the fiber. So if the crack initiates, they want to basically deflect the crack growth. They design the interface in such a way that the crack, when it reaches the interface, it propagates along it. In other words, it's not going to go through the fiber because the fiber carries the load, okay? So that's the idea here. So you have the matrix, the fiber, and then the interface. And so you have a pre-existing crack, and then you pull it from the top and the bottom. What's going to happen is this crack is going to propagate, it's going to go through and then hopefully deflect, right? So that's the problem. And so these are the governing equations we have. We're using the axisymmetric set of governing equations here. It's my displacement equilibrium equation, both in R and Z directions. And these are my boundary conditions. This is the stress-strain relationship, okay? So the material properties, lambda and mu, are Lamé's material constants. So then we rewrite these equations, right? All of these equations by using peridynamic differential operator. And these are my peridynamic functions, right? So we write everything in terms of the unknowns, the displacement components, U and W. U is the displacement in the R direction, W is the displacement in the Z direction. These are my stress-strain relationship. And here you can see the crack initiates, and then it's going to, right, before it reaches the interface, you have initiation, and then they coalesce, and then they propagate through. So the idea here is, what is the effect of, for example, the interface strength or the interface thickness? Okay, so the coating thickness here is 1, and here the coating thickness is 2. So you can see the effect of interface thickness. So in this case, the crack initiates as the main crack gets closer to the coating here. Okay. So in peridynamics, as I mentioned before, we don't have to worry about singularities because we don't take any derivatives. So there's no mathematical singularity. So here I have this linear advection equation, and here I'm going to show you how you can actually use this weight function to your advantage, so that the information travels in the right way. So that's my equation here. Then here you have the boundary conditions. These are periodic boundary conditions here as well. And then we discretize it. And here my horizon size is 2 times the grid spacing because the highest order derivative is first order here. So that's the solution we have. And as you can see in this particular case, I don't know whether I have, there should be a video here, but we'll see. Yes. Maybe I get out of this and then, okay, here. So you compare it against the analytical solution. Numerical dissipation exists, of course, but it's stable and really captures the characteristic speed. Okay. Anyway, so now during COVID, there's a history behind everything, right? So we were looking around to solve some interesting problems. Then I teamed up with these colleagues in Saudi Arabia and another colleague at MIT. So we said, okay, maybe we can apply the Peridynamic differential operator to Eikenal equations. So we looked at various types of Eikenal equations. And if you're interested in, we published a paper. It's in Geophysical Journal International. So this is a simple isotropic Eikenal equation that I'm sharing with you. And so T is the travel time. You have the source here. And this is a velocity field. It's known as Marmosy. And so we discretize this hyperbolic equation. It's time independent. And again, the horizon size is 2 times the grid spacing because the highest order derivative is 1 here. And we did very detailed study here. So here is the discretized form of the equations. It's nonlinear. So we use Newton-Raphson to solve these equations. And I can show you the comparison of peridynamic solution, reference solution, fast marching solution. So the reference solution is fast marching with very fine mesh. Okay? And so as you can see here, peridynamic solution really captures the sharp change in travel times around the region where you have the highest velocity gradient. And here I have the error measure, right? Basically, fast marching method and peridynamics. You can see it's about in the same order, and sometimes it's less. Okay, so that takes care of that. And then now I have another example that that shows you how you can basically construct solutions to a coupled field equations, multi-physics problems. And I picked this problem because it's the equations are complicated. And so this material that you have here, it could be a rock, for example. It could absorb, oops, I don't know why I jumped. So you could have shrinkage or swelling, depending on whether you're drying or you're absorbing. So you could have this moisture can basically seep through. You can have deformation due to moisture change. You can have very internal stresses. As a result, you can have formation of cracks. So the modeling challenge here is, of course, the coupled field equations. I don't know why it's doing this. Coupled field equations, but so you have crack initiation and crack growth in an unguided fashion, right? As you can see here, these are experimental. Right? And so these are the equations, governing equations for desiccation. So you have this transient flow in this unsaturated soil. I'm not going to go through the details of this. And we have the equilibrium equation, and they're coupled, okay? So all these variables are given here. I mean, there's no point going through the details of this. All I can tell you is, you can discretize this equation and this equation the way that I showed you before by using peridynamic differential operator. Everything remains the same. And here, this is our discretization for the specimen that Tang and his colleagues considered. And so we basically took the material properties, the parameters that we used in this simulation, all from this paper here. Okay, and that's our discretization. And we used, let's see, yeah, I think that's what okay, this is what I want to. So here you see these different colors, right? In the discretization. So what we did here is because we don't know where the crack is going to initiate, right? So we added some randomness to the material properties and to the critical value that we use for bond breakage. So So this represents some randomness in the material properties and the critical stretch value that we used in the bond breakage. And here you see the peridynamic predictions. And that's the horizontal cross-section of the specimen. This is the vertical cross-section. As you can see, again, other than the randomness, we don't do anything. It's just basically, we don't fine-tune anything, we don't change anything, everything remains the same. Okay? And as you can see, very nicely, it captures the crack growth patterns and how the crack initiates and propagates. Very complex. Right? Okay, so then the other problem that I considered here is where you have phase change, right? You have a moving boundary. So the first problem I showed you, multiphysics, you have crack initiation and crack growth, which is challenging because of the singularities that you may face. And now here, if you have, let's say, this galvanic corrosion, you're going to have these, so you're going to have material loss from anode, right? So electrons are going to be basically lost from anode, and you're going to have this, phase change. This aluminum is going to become electrolyte, and then you have this moving boundary here. So, so how do we model this? So it's a challenging problem, and so governing equations, we have this electropotential and concentration. So these are solved in a coupled way, and these are pretty well established interface conditions along the moving boundaries, and so we monitor the corrosion frontier. So as I mentioned before, the peridynamic bond that you have a status parameter. You can either kill it or you can give birth, right? So in this case, basically that peridynamic bond changes phase. So it becomes electrolyte, basically it represents the electrolyte here. So here I have the discretization. So I have the electrolyte, I have the cathode, I have the anode, right? I go through and solve these equations for each of these, and I can show you the electric potential. That's the peridynamic. This is the phase field approach. So as you can see, it captures the results. And I'm not going to say much more than that, because if you're really interested in this particular application of peridynamics for electrodeposition and for galvanic corrosion, so we have this recent paper. It describes in great detail the approach, how you can set up the equations, how you can monitor the crack front, whether it's material removal or material addition. So I will leave it at that. So my last sort of topic here is how you can use peridynamic differential operator for data recovery. Okay, so basically what you have is these blue points that I show you here. They are the points with some known values, and then the red one here, you don't know the value at that point. So basically, if you construct your peridynamic functions, right, for this particular point here, x, the red point, and in terms of the blue ones, so then you basically you're going to take the zeroth order derivative. You're going to try to estimate the value of this function here, right? Whatever is given to you, you're going to estimate that. So that's the idea. I mean, we're not doing anything different than that. So, okay, so each interaction is influenced by the number of family members. Okay, then of course this xk is the position of the point in the family. So we did write a paper on this in 2022, how you can use peridynamics for data estimation, image compression, recovery, and model reduction. So here's an example. So I have this image here. It has this many pixels. Each pixel is a peridynamic point. Okay, each pixel is a peridynamic point. And then we just said, okay, let's take 572 pixels, right? Basically, it's 0.1% or something. I don't know. So these white points that I show you here, they are the picked points. They're the values that we know. They are the pixels with values. The dark regions here, okay, I'm going to try to estimate by using peridynamic differential operator their values. So with 572 pixels, I can estimate, right, the values at the missing pixels. So this is what I get. So after I recover with the zeroth order peridynamic functions. So this is the global error measure is almost 10%. but with this many pixels. If I go to, almost half, and then what you have is, okay, you have this many pixels, and you can do this in an iterative fashion. Then you ask me, well, how do you pick these points? There's an adaptive scheme that we developed. So based on the error, I can go and pick more pixels, and based on that, I can recover. Now, based on this, I can recover the values at the missing points. These are the dark points here. So now my recovered pixels are about, less than 1%. So you can apply this to many different problems, but this is the one that I wanted to show you. And my next problem is this data reduction and compression. So it's the same idea. And here we take this Stanford Dragon. It's like a point cloud data. And it has this many data points, okay, almost 55,000. And this is from that particular website. Then we said, okay, the first iteration, right, we will take 0.2%. Okay, so this is the original that I showed you, right? It has 54,000 data points. Now I'm taking 0.2%. So the dots that you see here, I know the values, right? Those points. And then I use my peridynamic differential operator, basically the zeroth order function, and I get this image, right? At the unknown locations, I apply that. So the error is about 55%. So then I say, okay, let me take more data points, like based on what I know here, I'm going to take more data points. Now 5% more. I took 5% more. Now this represents the picked data points, right? Those are the picked pixels. So now I have about 2,800. Now I recover the error. It's about 52%. So it went down a little bit. Then I say, okay, let me take 5% more. So now it's 55,000. So these are the pick points. My error went down to 12%. I picked 5% more, 8,000. My error went down to 9%. As you can see here, the same idea. I'm up to 25%. My error is 4.7%. And now here, with 30%, right? 30% of these points, I recover this image here. The error is 2.7%. Okay. So this is what you can do. Then, of course, the idea is if I were to lose 70% of the data, right? 70% of the data. So can I recover this image that I have, right? Basically with 30% of the data. I don't know the locations or anything. So this is what I get, you see? This is the original. This is 30%. Now this is my recovered image. So I lost 70% of the data, and I'm recovering this image here. So this is a very nice application, and I think in my opinion, you can apply this technique for LiDAR data. So if you have LiDAR data, millions and millions of pixels, if you want to compress it, and when you compress it, you are losing some percentage of the data. It's not like file compression here. So you basically lose it, and then it goes to a different computational platform, and then with the 30% or with the 40%, you need to figure out what the original image looked like. So, and lastly, you can do data smoothing because it's non-local. It really works as a filter. So you can use it as a filter as well. And here's an image here. And if you apply this peridynamic differential operator and the zeroth order peridynamic functions, as you can see, it smooths things out because it's non-local. Okay. And here you have these tiles. Again, if you smooth it out, at least it gives you almost an image of a human face here, for example, from here to here. Right? So that you can use it as data smoothing and or as a filter. So I'll make some few remarks here, and then I will have enough time for questions if you have any questions. So basically, what I'm showing you is with peridynamic differential operator, really you can construct the solution to any type of partial differential equation, okay, without the smoothness requirement, and you don't need any special techniques. So you don't do any fine tuning. You don't do any special treatment of any kind. You basically apply the same strategy, same discretization to any of these problems you have. If you are interested in crack initiation, propagation, that's very suitable for that because then you can break the bonds. So it's a unified approach for multi-physics problems. You use the same single mesh, right, for different fields, and and you can have different time scales. Let's say if I'm looking at electromigration, then I will have different time scales. Okay, I didn't show you any of that, but you can. So that's a nice feature of that. You can have phase change, moving boundaries, and discontinuities. And in the case of data manipulation, it's very robust for compression and recovery. And it is a mathematical framework, right? I mean, there are so many different techniques that you see in the literature, but it's not a mathematical framework. Okay? So it's I use the same framework. I construct the paradigmic functions, and then I basically recover them. So it's the only thing that you control is the number of family members and the horizon size when you do data manipulation. And lastly, it's very suitable for GPU architecture for speeding up the computations, because each family member, you can assign a GPU and you basically perform your calculations that way. Okay, so and if you're really interested in learning more about peridynamics, so we wrote the first book in 2014. We didn't know much about peridynamics then, because the first paper came out 2000. We thought we knew what was going on, but then we said, okay, we learned more since then. So it's our first book. It's been translated to Chinese and Persian. And then the second book is on paradigmic differential operator for numerical analysis. As you can see here, different topics. And then we wrote another book on advances in peridynamics, where you have different material nonlinearities and sort of complex material models. And lastly, we integrated this peridynamics and its applications in a commercial framework. So you can do a lot of the analysis by using ANSYS. So through the macro files, we put everything together. And so you can use ANSYS to look at some of these problems. And those of you who are interested in submitting or writing papers or publishing papers, so we do have a journal of peridynamics and non-local modeling. We would be glad to receive your manuscripts, and we do hope that you consider this journal for your publications as well. So with that, I will stop. If you have any questions, I will try to answer.
Thank you for the nice talk. For questions, please raise your hands. You can unmute your mic as well if you have a question. Okay. Okay. I have some few questions. So all right. Very nice presentation. I was very happy to see the range of applications you had from all the way from engineering to image processing for non-local operators. That was nice to see. At least we got some few ideas where we could apply things. But I was I was a little lost on the details a bit. So all right. So let's start by, you had a notation where G was the peridynamic function. I assume so. So in that notation, there was a subscript and there was a superscript which had like numbers of 2 and 20. So I quite didn't understand what are those numbers.
Yeah, good. So basically, the subscript, right? The subscript is indicates where I truncate my Taylor series expansion. Like G sub 4, right? So I'm interested in up to fourth order derivatives, right?
Mm-hmm.
If the subscript is 2, then I'm interested in up to second order derivatives. Okay. So the superscript, if it's 1 or 0, let's say G2 1 0, that means I'm taking the derivative with respect to x1 once. That's it, right? If you have 2 0, that means I'm taking the derivative with respect to x1 twice. If I have 0 2, that means I'm taking the derivative with respect to x2 twice. So that allows me to distinguish the, I can go to presentation here.
But x1, x2 are different dimensions, or they are different points of the same domain?
Do you see my screen?
Yeah, I see it now.
So let's go to this example here, right?
Mm-hmm.
You see my screen?
Yes, I see your screen here.
Slide 10, right? Slide 10. So
Mm-hmm.
here, basically what you have is like, this is my, right? I have now, I'm truncating, and then I'm multiplying each term with a peridynamic function. You see G4 is the truncation. P is going to be either 0, 1, 2, 3, 4, right? It's going to give me the derivative of interest. If it's 0 function and so forth. So I have a peridynamic function for each of these. For G4, 0, I have one complete polynomial, as I showed you here, right? I have G4, 1, G4, 4. So I'm going to have these polynomials with those coefficients, right? I need to determine these coefficients from the orthogonality condition. They're coming from here.
I see.
Yeah,
I
so
see.
they're done. We do that once, and then you don't do anything else, right? So when we solve a problem, we basically discretize it, and then for each point in your domain, you construct your peridynamic functions. You do numerically, right? Because this, what I'm showing you in this slide, is for a point symmetrically located in a regular domain, so that I can perform that integration analytically. But I don't have that luxury. So let's say I go to, I'm looking at, for example, here, right? If I have a point here, so this is my domain, right? And this point X is symmetrically located. And the other nice feature of this approach is I don't have any ghost points, right? In most, like RTPM or some other non-local methods, you have ghost points, right? So you want to complete the support region or the domain of interaction. Here, it's basically non-symmetric. So for each point, I construct my peridynamic function. Once I'm done with that, I go back and take the derivatives and then rewrite my equations in discrete form, construct the algebraic equations, and then you solve.
Okay, so this will lead to me for every different problem. The function g will be different, right? Because satisfying the orthogonality condition, you will have. So this begs the question. All right, the framework is the same, but if I start computing my functions for a case where there is no crack, and then I want to predict a crack, how would I go about it?
So actually, that's a good question. So if you do explicit analysis, so what happens is as the crack propagates, as we generate new crack surfaces, we don't go back and reconstruct the peridynamic functions. We use the same ones. So that's a good question, right? So we don't do it that way. So for crack growth analysis, although I'm creating new surfaces, you are right. But if you do that, it's going to be computationally very, very expensive. In the examples that I showed you, we did not construct the peridynamic functions as the crack grows.
Yeah, but you might have some because the solution is, because it depends upon the solution. So the solution.
I know you're right, right?
Yeah.
I know you're right. I know you're right. So what I'm saying is, from a practical point of view, if I showed you that example where I have these multiple cracks, right? These things, right? Wherever this problem that I showed you. So this problem. And this problem here. So I didn't go back and on the fly. That means on the fly, I have to construct each of those peridynamic functions. You are absolutely right. If I have only one single crack, I can go there and, each time the crack grows, I can reconstruct the peridynamic functions. I can do all of that stuff. And you're absolutely right. But for this problem, to make it practical, I mean, we don't do it. That's what I'm saying.
Fair enough. So fair enough. So how do you figure out if that's the right function? Like you have you have some crack and like, okay, for let's say the first case, you have theta w equal to 0.388. That's where you construct your functions, and then you let it evolve, and the claim is that it works.
Say it again, please.
So
what
because So since it is very solution dependent, I'm actually having a bit hard time to understand this. So it's my mistake. So the thing is that, okay, you might have an initial state which is very indicative of your problem, and that's where you compute your peridynamic function, and then and once you compute your peridynamic functions, and then you let it evolve. Is this what you're
Yeah, I
doing?
mean, in the case of crack initiation and growth, right? That's what you do. But if I give you this Eikenal equation, right? So all I'm doing is I'm replacing the derivatives, local derivatives, with non-local representation. That's all I'm doing. I'm not doing anything else. Right? I'm just solving for the travel time. So it's not solution specific or problem dependent or anything like that. All I'm doing really is differentiation through integration. That's the key. It's very accurate differentiation through integration. And when I do integration, I don't divide anything. I don't care whether whether I have zero or not, right? I mean, I'm adding things up. So nothing blows up.
No, that's fine, but that's fine. You're replacing integer order operators with with an integral
Right.
differential operator, which has a peridynamic function embedded in it, and you need to know an explicit form of that particular function. So in order to have an explicit form of that function, what I'm asking here is that you might need an indicative solution. I'm not telling you that you need the actual solution, but let's say there is a feature that you want to extract. So maybe one of the cases where there is some level of crack, and that's where you compute your peridynamic functions, right? And then we continue evolving the solution. Uh, no?
No,
Yes.
no. The beauty of
No.
peridynamics, the
Hmm.
beauty of peridynamics is that I can break these bonds,
Hmm.
and that's all I do. So I'm showing you here the
Hmm.
mathematical representation of the peridynamic function. So if I look at the equations, which I
Hmm.
didn't spend any time, if I look at the equation of motion derived
Hmm.
based on the principle of virtual work, I don't construct any peridynamic functions there. I basically derive those equations based on principle of virtual work. Do you know what I'm
Fair
saying?
enough.
So yeah, that's what I'm saying. So the point here is that with this peridynamic differential operator, I recover the same equations that Silling derived in 2007 based on principle of virtual work, and he doesn't construct any peridynamic functions, right? I mean, we basically have bonds and bond properties. We break these bonds, and then we basically predict how the crack is going to initiate and propagate. So do you know what I'm saying? So the theory itself
I
is
get the high.
really
Mhm. Mhm.
okay.
I get the high level idea, but then I
Good,
will,
good.
but then I'll have to look
Yeah,
into your papers for exact details. Unfortunately, we have to cut short this discussion because we have a
sure.
second term. But in any case, it was really nice having you here. Thank you for the nice talk and for the presentation.
Sure. Thank you. Yeah.
Yeah.